Hi, I'm Philipp and I will introduce you to our work on 3D texture synthesis, namely learning a neural 3D texture space from 2D exemplars. For a given texture exemplar set, the goal of our work is to synthesize them. Such exemplars can be casually captured using a mobile phone. Prior works have been focusing on synthesizing single exemplars, but did not focus on creating a space of textures, whereas we do. Having a compact space of textures allows us to synthesize textures beyond the given dataset. However, the main contribution of our work is the synthesis of 3D textures, using only 2D textures as input. Having said that, there are a few more properties that our method enjoys. First, our method is able to produce diverse outputs given a single exemplar, and can also output textures of arbitrary size. As I said before, we create a smooth latent space of textures and are hence able to interpolate between exemplars. The synthesized texture can be sampled at any arbitrary resolution, which allows for zooming. A very important feature is computational efficiency. We can synthesize textures pointwise, which makes our method lightweight and efficient. Lastly, our work allows for 3D texturing, independent of shape and resolution. Let's have a look at our method. We are given an exemplar set Y. At each training step, a crop of a single exemplar is taken and encoded using an encoder G. The encoder G returns Z, which represents our compact latent space. Our latent space is then divided into two parts using a translator module H. It outputs a texture code E and a vector of learned transformations T. The texture code E can be seen as what kind of wood or grass is encoded. The vector of T's, on the other hand, is used to transform the coordinates before reading the noise that we are sampling from in the next step. Therefore, the noise function takes as input a coordinate x, the vector of transformation matrices T, and the random seed xi. Before we have a look at the noise function, let's dive a bit more into the translator function and its purpose. The translator allows for Z to be more compact as it takes care of operations that would have to be repeated for Z, but are the same for all x. In this example, a translator lifts Z from 3 to 8 degrees of freedom, or in other words, 2 times 2 transformation matrices with 8 degrees of freedom are parameterized by 3 parameters. Getting back to our architecture, the next step is to sample noise. Let's have a closer look. We sample noise at different frequencies. The first level produces a low frequency noise image, whereas the following levels increase the frequency. This is achieved through scaling the coordinates by different predefined factors. After applying the given transformation matrix from the translator function, we sample noise. Now we finally get to synthesize our texture. We feed stacked noise values for each sample location combined with the texture code E into a learned function f that returns a single color value. Note, during training we sample neighboring points in form of patches in order to apply statistical loss. In particular, we feed both the cropped input patch and our output patch to a pre-trained VGG network and calculate the gray matrix of the VGG features. On a more high-level view at this architecture, we can see that the latent code Z, the coordinate x, and the random seed allow us to control the synthesis of our texture. Hence, we refer to the encapsulated block as the sampler function S. If we only change the latent code Z and keep everything else fixed, we will get different texture variations, whereas if we keep Z fixed and change x or xi, our method will produce different variations of the same texture. The only question that remains is, how do we synthesize 3D textures if we have only 2D textures given? The answer is very simple. Instead of sampling a 2D position, we sample a position in 3D. For training, that means we randomly extract 2D slices along the 3 major axes and ask for the slice to be statistically correct according to VGG. We conclude that our method creates a compact space of textures, is computationally efficient, and allows for 3D texturing. Additionally, it creates diverse textures by design. However, our work also comes with limitations. So far, we can only handle stochastic, non-stationary textures. Eventually, we would like to produce BRDF textures instead of just RGB ones. Hence, the question arises, would it be possible to learn BRDF textures from flash images? Well, here's a glimpse of what this could look like. Further results and experiments are available online as well as code. If you have any questions regarding our work, please feel free to reach out to me. Thank you for listening.